What if the most dangerous part of this conflict is the part you cannot see? No explosions, no missiles lighting up the sky, no breaking news alerts, just systems slowly starting to fail. Ports begin to delay shipments without clear reason. Air traffic systems show small glitches that get dismissed as technical errors. Financial transactions take a few seconds longer, then minutes. Nothing looks like an attack. Everything looks like a problem. And that is exactly what makes it dangerous. Because by the time anyone realizes this is not random, the pressure is already everywhere. This is not the war you watch. This is the war you feel, through disruptions, delays, and instability. And right now, while the world is focused on missiles, ships, and military movements, a second battlefield is already active. Not in the air, not at sea, but inside the systems that keep everything running. To understand what is happening right now, you have to change how you define an attack. Most people think of attacks as visible events like missiles, drones, or explosions, something immediate and easy to recognize. But cyber operations work differently. They operate inside systems that are already running, often using existing access points, weak security layers, or hidden connections between networks. What we are seeing is not random hacking, but targeted pressure on critical infrastructure, the systems that keep modern societies functioning, such as energy grids, water systems, industrial operations, and logistics networks. At the center of these are industrial control systems, the hidden layer that manages real-world processes like electricity flow, machine operations, and resource distribution. When these systems are disrupted, the goal is not destruction but loss of control. Systems begin to behave unpredictably, slowing down, malfunctioning, or shutting themselves off as a safety response. On the surface, this looks like technical issues, but when it happens across multiple systems at once, it reflects a deeper pattern. Modern infrastructure is highly interconnected and optimized for efficiency, which makes it sensitive to even small disruptions. A minor error in data or control signals can trigger a chain reaction that spreads across entire networks. This is what makes the current situation important, not a single event, but a coordinated pattern of disruption that gradually reduces system reliability. Instead of one visible attack, this creates an unstable environment where operations become less predictable and pressure builds over time. And by the time it becomes clearly visible, the impact is already underway. To understand how these attacks actually work, you have to look at the layer most people never see, the operational systems behind infrastructure. These are not general IT systems like emails or websites. They are industrial control systems that directly manage physical processes. At the core of these systems are devices such as programmable logic controllers, which act as the brains of machines by receiving data from sensors and sending commands to motors, valves, switches, and other equipment. A cyber operation targeting these systems does not need to destroy them. Instead, it focuses on gaining access, maintaining persistence, and then subtly altering how these devices behave. This can be done by manipulating data inputs, changing control logic, or delaying commands in ways that are difficult to immediately detect. For example, a system might receive slightly incorrect data about pressure, temperature, or flow rates, causing it to make decisions that gradually disrupt operations. In other cases, commands can be delayed or executed out of sequence, creating inefficiencies, slowdowns, or safety shutdowns. What makes this approach effective is that the system itself appears to be functioning, but not correctly. Operators may initially interpret the issue as a technical fault rather than an attack, which delays response time. At the same time, attackers can move laterally within networks, identifying additional points of access and expanding their reach across interconnected systems. Because modern infrastructure relies heavily on automation and real-time data, even small manipulations can create cascading effects. A slight disruption in one part of the system can impact upstream and downstream processes, spreading instability across the entire network. This method is not about immediate impact, but controlled disruption over time. It allows pressure to build gradually while remaining below the threshold that would trigger an immediate and coordinated defensive response. What makes the current situation strategically significant is not any single disruption, but the pattern that is forming across multiple regions and systems at the same time. When similar types of irregularities begin appearing in different sectors, energy, logistics, communication, finance, and across different geographic locations, it stops looking like isolated technical issues and starts to resemble coordinated pressure. Modern infrastructure is globally interconnected, meaning that systems in one region are often dependent on or linked to systems in another. This creates an environment where even localized disruptions can ripple outward. When activity follows a pattern, it reflects intent, timing, and structure rather than randomness. Instead of one large visible event, what emerges is a distributed model of disruption, where multiple smaller actions combine to produce a wider effect. This makes detection more difficult because each individual disruption may appear insignificant on its own. But when viewed collectively, they form a clear signal. Pressure is being applied across the system, not at a single point. This is what transforms isolated incidents into a strategic environment, one where instability is not accidental, but gradually constructed. The effectiveness of this strategy comes from its ability to operate below the threshold of immediate escalation while still producing meaningful impact. Traditional military actions are designed to be visible, decisive, and attributable. They trigger responses quickly because their origin and intent are clear. Cyber operations, on the other hand, exist in ambiguity. When a system begins to behave irregularly, slowing down, producing incorrect outputs, or shutting down unexpectedly, the initial assumption is often that it is a technical malfunction rather than a deliberate attack. This uncertainty creates hesitation. Decision makers need time to verify, analyze, and confirm what is happening before responding. That delay is where the advantage lies. During that window, disruption can continue, spread, and deepen. Attribution itself becomes a strategic challenge, as cyber activity can be routed through multiple layers, making it difficult to identify its true source with complete certainty. This transforms confusion into a tool. Instead of forcing a direct confrontation, the strategy creates an environment where the opponent is constantly reacting, investigating, and trying to regain clarity, while pressure continues to build in the background. One of the most important aspects of this approach is the imbalance it creates between cost and impact. Traditional warfare relies on expensive assets, aircraft, missiles, ships, each requiring significant investment to deploy. Cyber operations, by comparison, require far fewer physical resources, but can target systems that represent billions of dollars in infrastructure and economic activity. This creates a strategic asymmetry. A relatively small action at the digital level can influence large-scale systems that depend on precision and stability. Because modern infrastructure is optimized for efficiency, it is often sensitive to even minor disruptions. A slight delay, a small data inconsistency, or a temporary loss of synchronization can cascade into larger operational issues. This means the objective is not maximum destruction, but maximum leverage. By targeting key points within interconnected systems, it becomes possible to amplify the effect of a small action into a broader outcome. Over time, repeated low-cost disruptions can accumulate into sustained pressure that is difficult to counter without significantly higher expenditure on defense and recovery. Defending against this type of activity presents a fundamentally different challenge compared to defending against physical threats. In traditional scenarios, there are defined boundaries, identifiable threats, and clear points of interception. Cyber operations do not follow those rules. They move through the same networks that legitimate operations depend on, making it difficult to separate normal activity from malicious activity in real time. Infrastructure systems are deeply interconnected, often relying on a combination of legacy technology and modern digital integration, which increases complexity. Many of these systems cannot be fully isolated or shut down for protection without disrupting their primary function. This creates a constant trade-off between security and continuity. Defense becomes a continuous process of monitoring, detection, and response rather than a single layer of protection. Even with advanced systems in place, vulnerabilities exist due to the scale and complexity of the networks involved. This means that defense is inherently reactive, often responding after disruption has already begun rather than preventing it entirely. The broader shift taking place is that cyber activity is no longer a separate or secondary aspect of conflict. It is becoming an integrated layer within it. Modern conflict now operates across multiple dimensions simultaneously: physical actions, economic pressure, and digital disruption. These layers are not independent. They interact with and reinforce each other. Cyber operations can weaken systems before physical actions occur, making those actions more effective. They can also amplify economic pressure by disrupting the systems that support trade, finance, and supply chains. This integration creates a more complex form of conflict that does not follow clear start and end points. Instead of defined phases, there is continuous activity across different domains, each influencing the other. The battlefield is no longer limited to physical geography. It extends into the systems that enable modern life and global connectivity. Looking ahead, the implications of this approach are gradual but significant. This type of pressure does not build in a single moment or through a single event. It accumulates over time, affecting stability at multiple levels. Systems begin to operate with reduced reliability. Small disruptions become more frequent, and the margin for error decreases. As pressure builds, the system becomes more sensitive to additional stress. This means that when a larger event does occur, its impact is amplified because the underlying system is already weakened. Instead of a sudden collapse, there is a progression toward instability, where the effects become more visible only after they have already spread. This makes response more difficult as the issue is no longer isolated but distributed across interconnected systems. The key takeaway is that conflict is no longer defined only by what is visible. It is also defined by how systems behave under sustained pressure. While attention is often focused on physical events, the underlying systems that support everything, energy, logistics, communication, finance, are being tested in ways that are less visible but equally important. These systems form the foundation of stability, and when their reliability begins to decline, the effects extend far beyond any single event. By the time these changes become fully visible, they are no longer isolated issues but part of a broader pattern that has already taken shape. The challenge is not just recognizing that this shift is happening, but understanding that it is already in progress.